So I went ahead and up here on the board put the kind of, I call it the onion sometimes. Down here is closer to the nucleus, and these are lower energies, and going up we're getting more higher and higher energies as electrons are here. Okay, so the term electron configuration is just what we looked at a minute ago on the internet with that P table. How are the electrons hanging out? That's the electron configuration. Now, last week's lecture about how many electrons can you put here, blah, blah, blah. Those rules are very important, and we're going to follow those rules to a T. But we're going to focus on electrons as they are collectively in their lowest possible energy state. So that would be this ground state. So here's where, actually, in this lecture, I have to kind of backtrack this whole thing. This is a simplified version of how each subshell is arranged by increasing energy. Honestly, and I can go ahead and show you what's going to happen here. See this 4s? The problem starts right here. I'm going to show you something called the arrow diagram, and energy-wise, 4s is actually between 3p and 3d, and I'll show you how that happens. And that's not the only one. It's like, well, I'll just memorize that. No, they all get kind of scrambled according to the lowest n plus L rule. So the n plus L looks like this. I'm going to go ahead and add a column, n plus L value for each subshell. Okay? So don't forget that the L's, whether it's an S, the L value is 0, P, the L value is 1, D, the L value is 2, F, the L value is 3. So if I start here with 1s, the N value is 1, plus the L value is 0. Okay, that's what the N plus L value means for that subshell. If I go up here to 2s, the N is equal to 2. Again, plus 0 because it's an S-type. 2p, the N value is 2. Now the L value is 1. So the N plus L value is 3. I'm going to go ahead and do 3s. The N is 3 plus 0 for the L because it's S-type. Okay. 3p, the N value is 3. Since it's a p, my L value is 1. So collectively, they're 4. That's the N plus L value. 3D, my N is equal to 3. My L value for a D is 2. So I got 3 plus 2 is equal to 5. 4s now, let's see, N is equal to 4. And since it's an S-type, L is equal to 0. So I got 4 there. So this is where actually this 4 inserts down here. It's the lowest N plus L value subshell first. That's why that happens. N plus L value of 4p would be 4 plus 1 is equal to 5. 4d, 4 plus 2 is equal to 6. 4f, and F-type is L value of 3. So we have 4 plus 3 is equal to 7. So those are the N plus L values we're talking about. So I have a word for it. It's called the off-bow method, where basically we start with the lowest allowed energy level, or lowest energy level possible to put electrons. Once we fill that subshell, then we move to the next subshell. We fill that subshell, we move to the next subshell. So we're building up. Okay. So we're building up. And like I said, the stuff we talked about last week with each orbital, which is represented by a box, can only accommodate 2 electrons, and if it is full with 2, they have to have opposite spins. So we're going to see that in today's lecture too. And we talked about subshell types. For instance, if it's an S, it has 1 orbital. If it's a P, it's got 3 orbitals. If it's a D, it's got 5, and it's F, it's got 7. So we're going to follow those. Now there at the bottom, it's saying, and it is true, that when more than one location has the same N plus L value, electrons will go to the lower N first. So as I've written these, we actually kind of see it happen right off the bat. Okay? See that the 2p and the 3s, the same N plus L value, so it's the one with the lower N. that gets populated first. It actually has lower energy. Now I'm going to show you something called the arrow diagram coming up, because you're like, I can't unscramble that. That just hurts my brain. There's something called the arrow diagram, which helps you know which subshell to go to next. And I would draw it all over the place. So like when we were finding homes for those 6 electrons, for instance, around a carbon atom, we're going to place the first 2 electrons in the 1s, and then the next 2 electrons in the 2s. Okay, we're going to kind of build up like that. All right. So this actually, if there's only 1 electron, we kind of have the subshells within the same principal energy level. They actually have the same energy. So that only works for a hydrogen atom. Okay. Helium and onward, and actually picking on lithium with 3 electrons. This is how then we kind of see the principal energy level. You see the 2, n is equal to 2, where you have the 2s and the 2p. Now they start to split a little bit. N is equal to 3, we have 3s, 3p, and 3d. They're splitting. 4 electrons, or no, jumping from lithium to sodium, from 3 electrons to 11 electrons. This is the sort of split we have going on. Clear up then when we're dealing with finding homes for 19 electrons. Okay. This actually kind of this last one is showing this situation here. So, all right. This is one of those things that it's almost easier to show you, and I've been showing you a little bit, this idea of making each orbital a box, and we use arrows to represent electrons. And they're either up, which is a plus 1/2 spin, or they're down, which is a minus 1/2 spin. So that's that last quantum number. Okay, well, I want to go ahead and make sure we're all on the same page. I think you guys had your homework had you guys doing some of this. So that would have an m sub s value of plus 1/2, and that would have an m sub s value of minus 1/2. All right. So let's do some electron configurations. And I guess you guys probably have these just ready to put in electrons. So the 1 electron around a hydrogen atom would look like this. Just 1 arrow in the 1s box. Helium atomic number 2, guess what? It gets to completely fill the 1s subshell with 2 electrons, 1 going up, 1 going down. Lithium, 3 electrons. Again, if we're doing the off-bow method, the first 2 go in the 1s, and then the third one begins then filling the 2s subshell. So kind of like what I did the other day, we're okay until we get up to here. And then we're going to have to use the arrow diagram. So we're still in here, so that's all fine. So then we go to beryllium, 4 electrons. So we put the first 2 in the 1s and the last 2 in the 2s, making sure that they have opposite spins. And then hop, jumping, and skipping, we're on to boron. Boron has 5 electrons. The first 2 go in the 1s. The next 2 go in the 2s. And then we begin putting electrons in the 2p. So we only need to put 1 electron there to make 5. Now carbon does something a little bit different. Remember we talked about, and this is kind of why it can do this, the word degenerate orbitals. Degenerate orbitals. Okay, it just means that they're all the same energy. It's kind of like if you have like 2 kids and you have plenty of rooms, you let them have their own room. And that's exactly what electrons do. So for carbon, it starts out the same as boron. So 2 electrons in the 1s, 2 electrons in the 2s. And then we need 2 electrons in the 2p, and they get their own room. They spread out in those degenerate orbitals. And actually, the next slide has this, and it's a wonderful vocabulary word to put on my test. That's an application of Hoone's rule. Everybody gets their own room if possible. Notice that they're what we call unpaired, and they have the same spin. So just like we saw when we were kind of petering out electrons in subshell type with multiple degenerate orbitals, if possible, we have them be unpaired, and they will have the same spin. So there's going to be times when your homework's going to ask you, or I might ask you on the test, to kind of think through how electrons are configured, and are they going to be unpaired? Are they going to have their own room? Or are they going to be paired? And the other day, remember when I put paramagnetic and diamagnetic on the board? Okay, that's kind of what we've arrived. If you have electrons that are unpaired, that makes a paramagnetic material. And if they're all paired, that's diamagnetic. Just something that kind of catches my eye. Okay, so after carbon, let's pick up after carbon. So nitrogen is atomic number 7, so the 7 electrons look like this. The first 2 are like helium. They go in the 1s subshell. The next 2 fill the 2s subshell. And then, so we need 7. So then actually the 3 after that get their own room. So that's it. That's what the 7 electrons around a nitrogen atom look like, all in their ground state.
So how do we know when they get their own room?
Well, this might answer your question now. Oxygen, we have to pick up one more electron, and we're going to loop back. Okay? So for oxygen, we're not going to start, we're not going to give them their own room. It's just like your family. You're like, dude, sorry, you got to share. Because we're not going to start a new subshell until we get 6 there. So does that make sense?
Is this where we get 8 electrons? And
We're coming to it. Yeah, we're getting there to 8. We're building up to 8.
When we're building up, we start at the bottom. And once we get to 2p, we fill out the positive electron for each box.
Right.
And then go back and fill the negatives until
Yes.
we go to the next.
Yep. Yep, because exactly what you said, here's oxygen. So they all get their own room at first, and then exactly what you said, Mike. Then we go back, and in our first room, we're just like, okay, got to buddy up. And so then we have what? In those 3 orbitals, we have 1 orbital that's where the electrons are paired, and we have 2 orbitals where the electrons are unpaired. So where does the next electron go for fluorine?
The second box.
Yep. Yeah. And actually, there's no difference between these degenerate orbitals. We just usually go from left to right. It really doesn't matter. So, yep. So fluorine looks like that. And this actually gets to what Shelby was saying. Now, with neon, of course, neon, we have arrived at the end of the period. That group at the end of the period we learned before are the rare gases, inert gases, not halogens, noble gases. They have 3 names. So for neon, we need to find homes for 10 electrons. The first 2 go here. The second 2 go there. That's 4. We need 6 more, and we can actually put 6 in any p type. So here we go. So they all got to be buddied up. And we'll be talking more about this, but you probably learned before the whole magical octet, and I think it's coming up here in a minute, but the NS2 NP6, okay, where we have basically 2 electrons here in 2s, sorry, yeah, 2 electrons there, and 6 electrons here in 2p. Of course, if we add 2 plus 6, we get 8. And that 8 electrons is that magical octet that, that atoms will lose electrons to get an octet, atoms will gain electrons to get an octet. Heck, atoms will even share electrons to get an octet. So that is a rare gas configuration. So the next thing I do is basically look at those same elements. By the way, there's 2 ways to say how electrons are configured, and it's exactly what we looked at with the P-table app. You can do the box and arrow, which is what we just did, sometimes called orbital diagrams, or you can use the spectroscopic notation. The box and arrow I'll call the hand cramp way, because my hand almost gets in a cramp making all those boxes, okay? This sort of notation is easier, okay, but it's got its limitations. So it's also called the SPDF method, and it's exactly kind of what I said a minute ago with regard to kind of the first two. The first number gives you the principal energy level of where that subshell is located, and then of course S is the subshell. So the 1s corresponds to this. Okay, the superscript tells you how many electrons are there. So 1s1 for hydrogen, helium would be 1s2. So these match directly the box and arrow notations we did before. 3 electrons around a lithium atom. Well, the first 2 go in 1s, so it's 1s2, and then the last one goes in 2s, so it's 2s1. So when you hear me kind of say, well, you'll get it, you'll catch on. So using this sort of notation for 4 electrons, it goes like this: 1s2, then I pause, 2s2. So my first things I say are the principal energy level and the subshell type. And then the last number I say is for the electrons there. 3 electrons around a boron atom, well, we said we have to start then on the 2p. So we have 1s2, 2s2, 2p1. This is where it starts to lose a little of information. So with carbon, we can't show Hund's rule. For carbon, we just simply say 1s2, there's 2 electrons, 2s2, another 2 electrons, and the last 2 electrons go in the 2p. So it's 2p2. We don't show them spreading out, but we got to know it is. Okay? All right. Nitrogen then has 7 electrons. So 1s2, 2s2, 2p3. And then we go on to oxygen. 1s2, 2s2, 2p4. We just keep adding one more electron kind of at the right there. And nitrogen, that was after nitrogen, it's oxygen, we have fluorine. With 9 electrons, 1s2, 2s2, 2p5. And can you see where, if we want to know how many electrons we've accommodated, all we got to do is add the superscripts. Okay, so that's 9 electrons. So that's 7a. Then, of course, then we bump up to the 8a element in that period, which is neon. And again, that complete octet we're looking for is right here. So it's 1s2, 2s2, 2p6. Voila! So this is that famous arrow diagram that I would suggest you draw on your unit exam. Now in my intro Gen Chem class, when they take this test, I have them for credit draw the arrow diagram. For you, you don't get credit, but it's a tool I would suggest you draw. So it looks like this. Think of it as in first you're going to do rows. So the rows look like this with the principal energy level. So you go 1s, and you line up your s's. So then you go 2s, 2p, And then you go to n is equal to 3. Of course, we have 3s, 3p, 3d. And we're trying to keep the columns lined up. That's the big thing. 4s, 4p, 4f. Now, we could go 5g, but we're not going to. Okay, we're just going to stop with the f types. So then we go all the way to energy level n is equal to 7. So then we go 5s, 5p, 5d, 6s, 6p, 6s, 6p, 6d, 6f, sorry. And then the last row, 7s, 7p, 7d, and 7f. Those things in gray there, I usually don't include. So you recognize those as subshells. So here's where the diagonal arrows come in. So we start at the top. The first 2 arrows only go through one subshell. So the first arrow goes through the 1s. The second arrow goes through the 2s. Now our third arrow is going to pick up 2 subshells, 2p and 3s, and they are directional. So the way we're going to use the arrow diagram is to basically complete one arrow, and then we go on to the next arrow, the top of the next arrow, which is in the upper right-hand corner. So it looks like the 4th arrow picks up 2 subshells, 3p and 4s. The next arrow picks up 3d, 4p, and 5s. The next arrow, 4d, 5p, 5s. The next arrow, 4f, 5d, 6p, and 7s. And then 5f, 6d, 7p, 6f, 7d, and 7f. So what the subshells have in common that are on a given arrow is they have the same n plus L value. For instance, if we want to find the arrow that has 4s and 3p on it, 4s and 3p, we said the n plus L value is 4. That's the way this arrow diagram works. It's not magic by any means. Okay? So these are the n plus L values that we talked about. But again, you start at the top of the arrow and you go down. Right away then, you can see that that's why, according to this the n plus L rule, we're going to go 4s before we go 3d. Okay, so let's do some. This is the way I think your textbook does it. It's similar. So let's use the arrow diagram to knock out how the 19 electrons around a potassium atom are hanging out. So this is the way it's going to work. The first 2 electrons, of course, are going to go in the 1s subshell. So I circle that here and I put them here. Sometimes students, and I'm not sure how I necessarily feel about this, but we'll kind of think of it as these all, we max out at 2 electrons. These P's, we max out at 6 electrons. The D's, they have 5 orbitals, so we'll max out at 10 electrons. You get the idea. The F's, we max out at 14 electrons. So kind of goes along with what we were talking about before. We got to fill that subshell, all the orbitals in that subshell before we go on to the next subshell. All right, so let's see. That one's done. We're on to the next arrow, which only has 1 subshell, the 2s. So we're going to put 2 electrons there. 2s, 2 electrons. So 1s2, 2s2. We've got 4. We're on our way to 19. According to our arrow diagram, we go next to the 2p. Sometimes we don't put enough stock in our arrow diagram, and then we get it wrong on the test. So 2p, and we need all 6 electrons, because that's only going to bring us up to 10, right? So 2p6 is where we go. And at this point, anytime you get 6 electrons in the p type, look back, and I bet you have 2 electrons in the s type. Okay, you have reached a rare gas. This specifically, this rare gas is in period 2, 2s2, 2p6. and that's neon. 10 electrons. So we only need 19 more electrons. So the next place is 3s, and we're going to go ahead and fill it up, 3s2. Looks like we're going to fill up the next one too, aren't we? Because let's see, 3s. Now according to our arrow diagram, we're going to go on to our fourth diagonal, the top. So that's 3p, and we need all 6 electrons, so 3p6. And again, we've reached another rare gas, and that rare gas is argon. So it looks like we only need one more electron. And where's that last electron going to go?
4s.
Yes, 4s. 4s1, perfect. And we're done. For each electron configuration, this is the spectroscopic notation, the way of notating it. The box and arrow would be a little more, like I said, kind of give you hand cramp. And remember I said that P table or whatever, and there's all sorts of apps out there, all sorts of interactive periodic tables. You click on it and they will tell you the electron configuration for the element. Let's do another one. That was 19, this is 40. Okay, so we're gonna go past, basically, we're gonna zoom past potassium all the way to zirconium. So first 2 electrons go in the 1s, so 1s2. Then we go 2s2, 2p6, and we have reached neon. So I'm actually going to kind of book all the way through argon. So then we go 3s2, 3p6, and we've reached argon, 18 electrons. And we only needed 1 electron in 4s before, but we got to keep going. So we're going to completely fill the 4s, so it'll be 4s2. Now where do we go next?
3D.
3D, exactly. And how many electrons are we going to put there?
10.
We are going to put 10. 3D10. Because 12 plus 18 is just 30. 3D10. And the cool thing about this little exercise is if you find the element with atomic number 30, basically that's how their electrons are configured. So that's like zinc. So we need 10 more electrons. Where do the next electrons go? 4p. And how many?
5.
So we're at 30 and we're on our way to 40. So 4p6. Yep. Because we max out at 6 and we need 10 more. So we can't go beyond 6. Very good. Now we've reached a rare gas. Which rare gas is this? Superman. Yep, this is krypton. So 36 electrons. So we only need 4 more electrons. Let's see, where we go next? Where do we go and how many electrons? 5s2. I'm liking it. Very good. Where do we go next and how many electrons? We'll need 2 more electrons, so.
6A.
Nope.
We only need 2 more.
2 more, but we're at the top of the next arrow.
So 4D.
Yep, 4D. Yep. 4D2. That's it. Yep. So if we had 36 electrons here, okay, so 36 plus 4, that puts us at 40, and that's what our goal was. Yeah. Now, I want to talk about something to kind of basically take how your electrons are configured and kind of unscramble them. So this is the order of filling using the arrow diagram. This is the order of filling. The unscrambling is basically what we call the order of an increasing n. Okay, so that's the order of filling. That should look just like what you had before. But increasing N, so do you see where, let's see, how do we got this? Everyone's a little bit different. You see where this 3 needs to go with these other 3s, and that will push this 4 with this other 4, and this 4 needs to come over, and that 5 needs to go over. So they're increasing principal energy level. So it looks like this. Do you guys have this? I'll read it off to you, okay? So 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d2, 5s2. Now, it might take you a minute to kind of look at it and to convince yourselves, but they are the same configurations. They're just kind of taking a whole subshell and kind of order them and increasing N. And here in a minute, I'm going to show you why you would care about that. What's the highest N? What's the highest principal energy level here? Is it 1, 2, 3, 4, or 5? Or 6, or 7, or 8? 5, yes. That's the highest N. Yep. So the electrons that are in subshells with the highest N are special. They're called valence electrons, which I know some of you have already run into before. Okay, so unscrambling in order of increasing N, okay, that actually exposes at the end your valence electrons. Valence electrons. They are special. Everyone wants to be a valence electron. Okay? Sometimes students will ask, well, Mrs. Snipes, if you have, and you will, I will have on the test where you have to do electron configurations, sometimes they ask, well, do I have to go ahead and reorder it increasing N? And the answer is no. Hurts my brain. But you need to recognize it and probably at least just pull out that 5s2 and know those 2 electrons are special. All right, that was 40. Let's do 53. We can do it. All right. So let's just kind of zoom on up to, because we did krypton before. Let's kind of do that. So it goes 1s2, and then it goes 2s2, 2p6. Then it goes, then we reach neon. Then it goes 3s2, 3p6, and we've reached argon. 18 electrons. After 3p6 on the arrow diagram, we said it goes to 4s2. Then we go to the next diagonal, 3d10, 4p6. And if you have a p6, you've reached another rare gas. This one's krypton. Now this is where we petered out last time, and we only needed 4 more electrons. But so we're on our way to 53. And if I would punch this into a calculator, so we still need, what, 17 more? Wait, on our way to 53. Yeah, 17? Does that seem right? Need 17 more. So where do the next electrons go, and how many? I think. 5s2, I'm liking it. That's 38. Where do the next electrons go and how many? Actually, Ms. Ruskell throws candy bars at people when they get the right answer. 4d10, yes. Very good. So now we're up to, let's see, 12 plus 36, we're up to 48. Okay, so 48, we still need, 48, we still need 5 more? 48 to 53, okay. Still need 5 more electrons, okay. That math's working, okay. So, what subshell do we go to next? 5p. And how many electrons do we put there? 5. Yep, 5p5. Ding, 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 ding. Whew. Does that sound okay? So the green says that's in the order of filling. So on this slide then, I'm going to go ahead and unscramble them in the order of increasing n. So it goes like this. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, and then 5s2, 5p5. So what's the highest n? N is equal to, what's the highest? 5. I see a hand symbol up here, 5. Yep. So how many valence electrons are there?
7.
There are 7, because these are valence electrons and these are valence electrons. 7 happy valence electrons. Very good. Now, is this where I think I talk about, yeah. So there is this shortcut, and we all love shortcuts. So it's optional. The problem with shortcuts sometimes is they bring with them a danger that you'll get the wrong answer or you'll write it down wrong. So the shortcut goes something like this. Whenever you reach a rare gas, actually you can write that rare gas in brackets, okay? And it's the latest rare gas. So on our way to 53 electrons, the last rare gas we passed was krypton. I can tell by just looking at the periodic table, because iodine is in period, what is that, period 5? Iodine is period 5. The period 4 rare gas is krypton. So what we would do is basically write Kr in brackets, and then everything beyond Kr. So I'm going to go back up to this one. So Kr in brackets represented this much. So Kr in brackets represented all of that stuff up to 4p6. So personally, I probably would write it like this. Kr, and then I would write 5s2, 4d10, 5p5. That's probably how I would write it. Just because I would go right from kind of the as. Okay. But notice that these are the same, just kind of in, this one is more in order of filling, and this one is order of increasing n. They're the same thing. Okay? Cool. What else we got? So the abbreviated rare gas form. There are some rules. One is that it has to be the rare gas in the period immediately before it. That's probably the biggest rule. All right. Cool. Not sure what this is supposed to be. Oh, I see. I'm adding the, like 2p6, you've reached neon, 3p6, you've reached argon, 4p6, you've reached krypton, xenon for 5p6, radon for 6p6. And at the time this was written, the rare gas in period 7 did not have a name. I'm not sure if it's, I think it might be named now. Okay, so the arrow diagram will always get you the right answer. There's actually, I'm going to show you something else, how to take the periodic table and chunk it up. You'll need to know kind of the chunks of the periodic table, but also we can use that as an alternate method of getting how electrons are configured. I'll try to walk you through that. So you recognize that hopefully, well, I shouldn't say that. Some people might be colorblind. Okay, but we do have 4 different colors here. We have this pink, kind of this light blue over here, a tan, and kind of a gray down here. And each color actually represents a block in the periodic table. So the first block is what we call the S block. The pink is the S block. Okay? So The blocks actually represent where if you're coming up with how electrons are configured, that's the sort of electrons that are being added to or kind of petered out, okay? So for instance, you can kind of see sodium and magnesium up there, okay? Like these guys up here. They're both S blocks. Specifically, they're in period 3, so they're 3S. So actually, I know right away, and I don't mean to like make it look crazy easy, but if I wanted to say how the electrons, or 12 electrons around a magnesium atom are configured, I could actually go to the rare gas, the rare gas in the period before it, neon. I could write that down, and then beyond neon, I could say there are 2 electrons, because I'm skipping across the S block twice, specifically 3S, and there are 2 electrons like that. I could come up, and that's actually magnesium. Okay, so that's how that works. Of course, then over here, the blue, these guys are P block elements. So let's do a similar thing for picking on gallium. Okay, so gallium actually is going to peter out electrons in the 4p subshell. If I wanted to say, oops, I'm not going to pick on gallium. Let me pick on something that doesn't go through the D block. Let's pick on aluminum. If I wanted to say how the 13 electrons around an aluminum atom were configured, I would go to the rare gas in the period before. I would write neon. And then I would hop, jump, and skip across to aluminum. So I would go here, okay. As I'm doing over here, I'm entering 3s electrons, specifically 2 of them, because I'm jumping twice. And then I peter out here, 3p, how many electrons? 1. Okay, so that's actually how the 13 electrons around an aluminum atom are configured. You get the same with the box and arrow notation, which works pretty good. The tricky part comes when you cross the transition elements, the transition or the inner transition. So these guys, these tan guys right here, are D block elements. So as we actually are finding homes for electrons, those guys, we will be adding D type electrons. But notice it's not N, it's not the period, it's N minus 1. So then, how that works, so for instance, is if we pick on iron, okay, iron is clearly D block, 26 electrons, and notice that it's in period 4, but it's 3D, so period 4, 4 minus 1 is 3, so they're 3D electrons. So that's why they call it N minus 1. So if I wanted to pick on iron, I actually would have to go to the rare gas in the period before it, which to me looks like argon. So for iron, it would look like argon, and then beyond argon, I kind of visually think of skipping across here. These 2 electrons would be what? 4s. And then I enter the D, specifically the N minus 1D, so that's 3D. And how many electrons? 1, 2, 3, 4, 5, 6. 6. Now, it looks cool, it looks easy. The arrow diagram, as I said before, will always get you there. This, not necessarily. And I'm not going to do it for I hate going through the F block elements. But the F block are the inner transition elements. I always get out the arrow diagram when I have to do anything down there, because it's N minus 2, and I just find it quite annoying. But if anybody talks about F blocks, they're talking about these elements down here, and it's N minus 2. So for instance, these guys are in period 6, okay, but they're 6 minus 2, they're 4F. Period 7, 7 minus 2 is 5F. So we actually have come to a good spot to go ahead and assign you that assignment that's at the end there. Let's take a look at then what's going to be due on Monday. So assignment slides should look something, well, you know what I mean, Wednesday. Let's not have to repeat days here. So it starts with
877.
877. It looks like this. And they're kind of fun in an odd sort of way. Okay. Okay, so which of these is, this is, to me, it's kind of like an overlap with what you already did. Okay, see what kind of hints I gave. Only one of these follows the rule of quantum numbers. So for instance, you would say A is bad, right? Because they're not opposite spins. And hopefully by now you would say C is bad because they're not spreading out. Okay, so only one of these is right. So that narrows it down to B or D. And I'll just kind of leave that for you. Each of these have 42 electrons. Explain what's wrong. Which of the following, which is correct and what's wrong, which are wrong. All right. So 79 right electron configurations. I would suggest the box and arrow to go ahead and answer these. We talked about unpaired electrons, Hund's rule. So I think that's probably how you're going to have to do this. Oh, I printed these off for you too. Well, they're on the printer there, outside. So anyway, this actually is, without looking at the periodic table, answer these questions based upon what we talked about, kind of chunking up the periodic table. Bless you. I think you should be fine for these. I'll push these hints out there. Don't worry about 84 if you don't want to. So 84 you can hold back, but it just talks about valence electrons. We'll hit those again on Friday. So I'll pull 84, but. So for these, I said don't do box and arrow, do the spectroscopic, the SPD and F. Oops, there's one more page. Are you serious? Oh, this one's not too bad. This one's pretty easy. Of all of them, these actually, they give you electron configuration, but you're just supposed to say what element it is. So to me, you just add up electrons, okay, and see what element it represents. Neutral atoms. All right, that's all I got.